Dirichlet's natural log of 2 equals half the natural log of 2 problem, presented by Simon Cox. Dirichlet discovered in 1827, while working on finding conditions to ensure convergence of Fourier series, a rearrangement of the series expansion for the natural log of 2 could lead to a surprising result, that the natural log of 2 could equal half the natural log of 2, or 2 equaled 1. He did it in the following way. Take the expansion for the natural log of 2 and divide it into 3 groups. Regroup the items. Evaluate bracketed terms and factor. Therefore, the natural log of 2 equaled half the natural log of 2. Using the method of partial sums with rearrangement, we will analyze what is happening. Our target rearrangement is this. The first partial sum is rearranged and split into the target and remnant series. The second partial sum rearranged and split into the 2 series. The third, fourth, fifth, sixth, and here is a list of all of the partial sums up to the 16th which have been rearranged and split into the target and remnant series. Patterns found in the target and remnant series are as follows. These can be expressed in terms of the Ki as follows. Looking at the target rearrangement T of Ki, we have the limit of the upper bound of the sum limiting to infinity equals infinity. Therefore, the limits of the sums all equal each other, as the summand for each sum is the same, and in each expression they start with the same index. Therefore, the limit of our target series is equal to half the natural log of 2. This is what we expect for the target series. Now looking at Rn, we see the summand is the same for all R of Ki and has this form. We can ignore the difference in start index as we will be comparing R of n and R of n minus 1, i.e. is the value of the summation increasing or decreasing. We take the difference of Rn minus R of n minus 1 and we evaluate. We conclude that the difference is greater than 0 and therefore R of Ki increases as Ki limits to infinity. We now investigate if each R of Ki converges or diverges to the same limit. Now R of K3 equals R of K4. So we will compare R of K3 with R of K1 and R of K2. We're going to use the same limiting value of n for K1, K2 and K3. We take the limit of the difference of R of K3 minus R of K1. We evaluate. And we see that the limit of the difference goes to 0. So R of K3 limits to the same value as R of K1. We now take the difference of the limit of R of K3 from R of K2. We evaluate. we see that the limit of the difference goes to 0, so the limit of r of k3 equals the limit of r of k2. So the limits of all of our remnant series all limit to the same value. Our original expression, the expansion of the natural log of 2, was rearranged and evaluated to the limits, these two limits, and we know the limit of the target set is half the natural log of 2. This implies that the limit of our remnant set equals half the natural log of 2, which implies that the limit of this sum equals half the natural log of 2. We can test this numerically. Half the natural log of 2 has this value, and we can compute the value of our summed expression and calculate the error from this value. And as we can see, as the number of terms in our sum increases, the error in our calculation goes down. Therefore, we can conclude that the sum of this series does equal half the natural log of 2. So the manipulation of the series expansion of the natural log 2 has resulted in the until now unknown generation of an ethereal series, the limit of which has infinitely many elements of infinitely small size that sum to a finite value. This is similar to integration. This completes our analysis of Dirichlet's natural log of 2 problem. See in the description below links to other videos that use this method to highlight errors in manipulating infinite series. These videos are based on a technical paper entitled Re-establishing the Additive Commutative Law for Conditionally Convergent Series. A link for this can be found in the description below. If you like this video, you may wish to subscribe to be notified when new content has been uploaded.